A very good afternoon to all the participants who are attending this course on nuclear science and technology. Dr. A.V.R. Reddy had delivered 6 lectures on radioactivity, nuclear decay, and nuclear models. And after that, I'll be taking the 6 lectures on nuclear reactions and production of radioisotopes. So I will just giving a background to this subject of nuclear reactions. Why the subject of nuclear reaction is important? It is important from many aspects. One of the main aspects is the production of isotopes itself. You want to produce radioisotopes, you need to use the help of nuclear reactions. And therefore, it is important to know the basic fundamentals of nuclear reactions, how the different projectiles like neutrons or charged particles or even photons induce reactions. And also you can, after this lecture, like the series of lectures, you will be in the position to identify the nuclear reaction that you can use to produce a particular radioisotope. That is one of the objectives of this one. Another objective is that the subject of nuclear reaction is utilized in nuclear chemistry or nuclear physics for many aspects. For example, right from the 19th century, the various discoveries that have taken place in the field of nuclear science, many of them, in fact, majority of them have come about using the nuclear reactions. So I will just give a brief historical account of the development of the subject in the early 20th century that led to this branch of nuclear science. In addition to this, if you want to study the structure of nuclei, then you need to bombard the nucleus with different projectiles so that you can study the structure of nuclei. So the subject of nuclear spectroscopy also arises from the nuclear reactions. So the basic requirement is that we need to understand the mechanism of nuclear reactions when we are carrying out any activity by like producing radioisotopes or studying the structure of nuclei. So I will give a brief background, the historical account of the subject of nuclear reactions, particularly in the early 20th century. The subject has really advanced after that. Subsequently, I will come to the basics of nuclear reactions, wherein what are the conservation laws that govern the nuclear reactions. So for example, if you want to write a nuclear reaction, we have to take cognizance of certain laws and that write the nuclear reaction. After that, I will cover the energetics of nuclear reactions. What are the types of energies involved in nuclear reaction? And depending upon the energetics, you will find that you can have different consequences. Sometimes you may have to supply energy like endothermic reactions. Sometimes the energy is released like exothermic reactions. In nuclear reactions, we don't call exothermic or endothermic, we call exoergic or endoergic. And then subsequently, I will discuss just touch upon the cross sections of nuclear reactions, and the details of the cross section part I will cover in the next lecture. You please do write your name and affiliation in the chat box so that we know that you have attended this lecture. And also, if you have any questions during the course of this lecture, do write in the chat box. I'll be happy to answer that. And if you are not able to write during this course, you can write an email to me, which I had given in the beginning of my presentation. Okay, so let us just touch upon the history of nuclear reactions. And as Dr. Reddy discussed in his first lecture, the very first experiment to even probe the structure of atom was by Ernest Rutherford in 1911, where he bombarded the metal foils with alpha particles emitted by naturally occurring radioisotopes like radium and polonium, radium-226, polonium-210. And based on the number of alpha particles that are scattered in the forward direction or in the backward direction, he concluded that at in the nucleus at the center of the atom, in a very, very small volume, roughly if the atom is like a football ground, then the nucleus is like a football. And so this was an experiment of far-reaching consequences in the field of nuclear science. I'll come to another experiment of this type, which happened in the 1960s, and which opened another chapter in the subject of nuclear science. So in the words of Rutherford himself, when he observed this, the backscattering of some of the alphas at almost backward angle, he wrote, it was quite the most incredible event. It was almost as surprising as if a gunner fired a shell at a piece of tissue and the shell bounced back, right back. And this was published in philosophical magazines in 1911. So the very discovery of nucleus itself arose from the inquisitiveness of Rutherford to bombard the metal foil with alpha particles. So if you want to understand a particular object, we need to bombard it with some different probes. And we have now many probes at our disposal. But at that point of time, these alpha particles emitted from naturally occurring radioisotopes were the only probes that were available. Subsequently, in fact, this particular reaction was not a nuclear reaction, because you can see here that was mainly the scattering of the alpha particle by the nucleus. So it's a Coulombic interaction. So when we say nuclear reaction, it is the nuclear force coming into picture. So the two objects, like a projectile and a target, here the alpha particle and the nitrogen-14, they come under the influence of nuclear force of each other, and there could be exchange of particles between them. For example, in this reaction, which was the reaction by which the proton was discovered by Rutherford in 1919, the protons produced fluorescence at a screen. And so Rutherford concluded that there are positively charged particles in the nucleus and called them as protons in 1920. But you can see here that this oxygen-17 that is produced is not radioactive. It is a stable isotope of oxygen. So nuclear reaction subject started, but not for production of radioisotopes. Later on in 1932, James Chadwick, the student of Rutherford, carried out these experiments of this type, alpha particle bombardment with different different targets. And he concluded about one of the radiations, highly penetrating radiations, which was assumed to be a gamma rays by some of the workers, but then he conclusively proved that this is not a photon, but it is a particle from the energy, the range, and the interaction, that is a neutral particle. And so he concluded that this is a new particle which is neutral, and it is a nuclear particle. James Chadwick received the Nobel Prize for this particular discovery. And again, you can see at that time, the alpha particles from polonium-210 were used as a projectile to bombard the nuclei. In the decade of 1920s, it was being felt that if you want to bombard the heavier nuclei and induce a reaction, then you have to have higher energy charged particles. And it is because of that reason, attempts started to accelerate the charged particles in different types of machines. And so that this particular decade between 1920 and 30 led to development of different types of accelerators. For example, in 1927, Cockcroft and Walton developed a voltage multiplier to accelerate the protons. Like we have a voltage multiplier tube where we multiply the electrons. He made a cascade of potentials by which he could accelerate protons. Van de Graaff at Princeton University developed an electrostatic accelerator to accelerate protons. So it's a one-step acceleration. You charge a terminal, and then the ions that are created from the ion source, they are accelerated to this high potential. And suppose Q is the charge, V is the potential, Q into V is the energy of that ion. So Van de Graaff could accelerate particles, protons, alpha, but could not lead to very high energy particles. Lawrence in 1929 at Berkeley developed the cyclotron. So by cyclic acceleration, one could go to very, very high energies of these charged particles. And subsequently, maybe you know that there were different types of accelerators, like linear accelerators, LINAC, where you accelerate the charged particles in a linear fashion in the LINAC tubes, drift tubes, where the gap between the two accelerating tubes increases, and the length of the accelerating tube. So it is like a cyclotron, but not cyclic, but linear. Also, a class of accelerators called pelletrons were developed later on. Pelletrons are like tandem accelerators. You start from negative ion, accelerate to a positive terminal, strip the ions of electrons, and then further accelerate the positive ions from a positive terminal to the ground. So there have been now a lot of developments in producing high energy charged particles, so much so that we have now hundreds of GeV of charged particles produced to study the subject of nuclear science. Okay, subsequently in 1934, in fact, the very reactions that were used by James Chadwick to discover the neutrons were also being studied by Irene Curie and Frederick Joliot. And in 1934, they observed that when the alpha particle bombards aluminum-27, though the neutron is produced, the product, the residue, phosphorus-30, is a beta plus emitter. And so this was the first time that a nuclear reaction leading to formation of a radioisotope were known. And that is how the Irene Curie and Frederick Joliot received the Nobel Prize for the discovery of artificial radioactivity. So this is the beginning of production of radioisotopes. And as you know, today there are more than 2,000 radioisotopes that have been produced, and many of them are finding applications in many, many areas, which will be discussed in subsequent lectures. Along with this discovery and that of neutrons, there were many scientists trying to unravel the mystery of nature. And once the neutron became available as a projectile, Enrico Fermi in 1934 started bombarding different elements with neutrons. And the familiar reaction that he found that after capture of neutron by a stable isotope, and then there is a gamma ray emission, there is a next isotope of that element, for example, sodium-23 N gamma, sodium-24, and that is undergoing beta minus emission to give a next higher element. So the isobar of higher Z. Similarly, cobalt-59 N gamma giving cobalt-60, which is undergoing beta minus decay to give nickel-60. So you can see here that these reactions are giving element of higher atomic number, next atomic number, next element in the periodic table. And so this led Enrico Fermi to conjecture that if he bombard uranium-238, then he should be able to produce element 93. With that objective, he bombarded uranium with neutrons so that you get to 39 uranium, and which upon beta minus should give you to 39 element 93. And so therefore, the objective of these experiments was to extend the periodic table beyond uranium, which was the last element known at that point of time. But then this group of physicists, Enrico Fermi at Rome, they've observed that there is a large number of radioisotopes formed in that reaction, and then you require a chemistry person, a radiochemist, to separate these different half-lives, identify them. So it became a puzzle to solve, which this group was not able to do. And then this activity shifted to Paris and Berlin. The two strong groups started exploring this particular reaction of neutron-induced reaction on uranium. Now, what was the people are discussing that if you bombard uranium with neutrons and it goes to a higher atomic number, element 93, that will be emitting alpha particles. So by emitting alpha particles, these elements will go to lower atomic number elements. So from uranium you go to thorium, from plutonium you go to actinium, for thorium you go to radium. So they were looking for separating radium, actinium elements in the reaction products after bombarding thorium and uranium with neutrons. Now radium and actinium are radioactive. So how do you do separation? What they were doing, they were using the lighter homologs as carriers. So to separate radium, you use barium and separate barium compounds like barium nitrate, barium sulfate, barium carbonate. To separate actinium, they were using lanthanum as a carrier, and so you can separate lanthanum as a fluoride or oxalate and so on. So the Irene Curie and Frederick Joliot group, they wanted to separate actinium, and they found that one of the activity was separated with lanthanum as a carrier. Now they are observing fission, but they are not able to conclude that they have produced lanthanum. Instead, they concluded that it is the actinium isotope that are produced in bombardment of uranium by neutrons. Then come the very clever experiments by Otto Hahn and Strassmann in 1938. And in fact, these are one of the finest radiochemical experiments ever done. So they were concentrating on the radium activity, and that radium activity, that time they used radium-226 as a carrier, as a tracer for radium, and they also used barium to precipitate this activity. So you wanted to confirm whether this is barium or radium. So what they did, they used fractional crystallization of barium and radium fractions. Now they found that the so-called radium activity was fractionated with barium fraction, which was very, very difficult to expect at that point of time because fission was not known. So Otto Hahn published a paper, wrote that bombardment of uranium with neutrons gives barium isotopes. Now this is a very, very path-breaking announcement that how can a heavy nucleus split into two fragments of lighter mass. In fact, just to give a brief more introduction, Lisa Mittner was working with Otto Hahn in Berlin, and she had to leave Germany went to USA, and he communicated the results to Lisa Mittner, and Otto Frisch, her nephew, in fact, they proved that yes, they are fission products because Otto Frisch could see the pulses of fission fragments in his ion chamber. So this is how the nuclear fission process was discovered, that uranium splits into two fragments upon bombardment with neutrons, and Otto Hahn received the Nobel Prize for this particular discovery. Lastly, just to close the historical aspects of the nuclear reactions, I was telling that in 1911, Rutherford bombarded different metal foils with the alpha particles to know the structure of an atom. In 1964, because by this time, a lot of particles have been discovered, different mesons were being discovered, and things were not very clear. So Murray Gell-Mann and George Dewey predicted that these nucleons, protons and neutrons, which are together called as nucleons, being the nuclear particles, they predicted that the nucleons are not elementary particles, but they are also made of finer particles called quarks. And this required an experiment of bombarding these nucleons with the 10 GeV electrons. In 1969, experimentally, it was found that the nucleons, like now how it was possible, because the wavelength of these electrons was much less than the dimension of the nucleus. In fact, its dimension is less than the dimension of protons. So the wavelength of the particle is an important parameter in investigating the structure. So such a small 0.02 Fermis, 1 Fermi 10 power minus 13 centimeter. So these experiments proved that the proton and neutron are consisting of some structures inside, which were found to be later on found to be quarks. So like proton is made of UUD quark, neutron is made of UDD quarks, and so on. And so Murray Gell-Mann received the Nobel Prize for this classification of elementary particles in 1969. So you can see here that the nuclear reactions, these are the studies which ultimately lead to unraveling the mystery of nature. Okay, so having discussed the historical aspects of nuclear reactions, let's come to the basics of nuclear reactions, that certain laws the nuclear reactions follow. So we will call a particle which is used to bombard the target as projectile, denoted as small a, and the target is denoted as capital A. Now the projectile and target react together, and in the process there can be emission of a lighter particles, small b, and leaving a heavy residue called capital B. So this reaction can be denoted in this way: capital A, bracket A comma B, bracket closed, capital B. So here in the quantities in the bracket are projectile and ejectile, and outside the bracket are target and residue. For example, the first reaction, helium bombarding nitrogen 14, giving to proton and oxygen 17, we can write as nitrogen 14 alpha P, oxygen 7. So that is how we have to write any nuclear reaction. Now these nuclear reactions follow certain conservation laws, given listed all of them here. The nuclear charge in any nuclear reaction is conserved. That means before and after the reaction, the total number of protons remains constant. So delta J, sigma Z is constant. You can see here in this reaction, nitrogen plus alpha 7 plus 2 is 9, proton plus oxygen 1 plus 8 is 9. So the proton number remains constant before the reaction, after the reaction. Similarly, the mass number remains constant, sigma A. Here this is not the target, this is the A for mass number. So you can see here the mass number of 14 plus 4, 18, mass number 1 plus 17, 18. Now you can see the corollary, that the proton number is constant, the mass number is constant, naturally the neutron number also remains constant. So you can see here that the protons, neutrons do not change their identity, they remain. It is the very small differences in the binding energy of these nuclei that is the energy that is involved in nuclear reactions. So if you want to burn a proton, then the energy equivalent to a mass of a proton is 931 million electron volt, 1 atomic mass unit. So what you see here is the small differences in the nuclear masses that are the energetics of the nuclear reaction, which we will discuss soon. Thirdly, the mass alone is not conserved. So here I am saying mass number is conserved. The mass is not conserved. Atomic masses or nuclear masses are not conserved because nuclei are being changed from one to other. So their masses are not same. Their masses are changed. But then mass and energy together are conserved. So this we can write in a general equation. I switch to M1, M2, E1, E2. That is for a projectile having mass M1 and having energy E1, and target having mass M2 and energy E2. Going to a reaction products M3, M3 and M4 and their energies. So this is the energy conservation between mass and energy conservation. And we can rearrange this equation into masses and energy. So M1 plus M2 minus M3 minus M4 equal to E3 plus E4 minus E1 minus E2. And that is called the Q value of the reaction, or the energy of the reaction. So we develop this concept of Q value from this mass and energy conservation. The Q value, if it is more than 0, it's called exergic reaction. The energy is released in this process. And if Q is less than 0, it's called endoergic reaction. Energy is required to carry out this reaction. This is different from enthalpy of chemical reactions. For exothermic reactions, enthalpy is negative because we say product minus reactant. Whereas here it is the reactants minus products. There is slight difference in that terminology. Another quantity that is conserved in nuclear reactions is the linear momentum. Mass into velocity is momentum. So momentum of projectile plus mass or momentum of target. So this is the total momentum, linear momentum before reaction is equal to that of the products after the reaction. The angular momentum is also conserved in nuclear reaction. I have written here in very simple terms the spin of projectile and target and the orbital angular momentum between the two. So it is not necessarily plus, it could be plus minus also, because angular momenta are vector quantities. They can add vectorially in different ways. So the initial angular momentum, sum of the spin and orbital part, is conserved after the reaction. In addition to these quantities, another quantity is parity. Parity, Dr. Reddy explained, it is just like the nature of a function, or in the cell model you must have come across S orbital is having even parity, P orbital is odd parity, D orbital is even parity, and so on. So parity is -1 to the power L, where L is the angular momentum. And so the parity is conserved before and after the reaction. And similarly, the statistics, like we have the fermions, which follow Fermi-Dirac statistics, and the bosons, which follow Bose-Einstein. So the statistics also is conserved before and after the reaction. Now let's discuss the energetics of a nuclear reaction. I will discuss in more details because these are the foundations of the nuclear reaction. Many of the expressions that we derive in this particular lecture will be useful for many more lectures, and therefore I thought I'll spend a little more time. So let us consider a projectile of mass m1 and energy E1 bombarding a target of mass m2, which is at rest. Naturally, this target is stationary, and they may amalgamate into a sort of a compound nucleus or a composite nucleus, and subsequently it can give two particles, like a projectile M3 and the heavy residue M4 with energy E3 and E4 at different angles. So M3 goes at theta angle and M4 goes at pi angle. So essentially we are studying the kinematics of this nuclear reaction, and we will derive some important formulae from this exercise. The exercise is nothing but solving the equation of conservation of mass and energy and linear momentum. The mass and energy conservation equation I had shown in the previous slide. M1 plus E1 plus M2. Now E2 is not there because E2 is 0, equal to M3 plus E3 plus M4 plus E4. This is equation 1, and from there we can write Q value. Q value equal to M1 plus M2 minus M3 minus M4 or equal to E3 plus E4 minus 1. And the linear momentum has to be conserved in the direction parallel to the beam and perpendicular to the beam. So parallel to the beam direction, the component of linear momentum in this direction is root 2 M1 E1 for the projectile. M2 is stationary, so no momentum. And for this M3, the parallel to beam direction, root 2 M3 E3 cos theta plus root 2 M4 E4 cos phi. This square root goes up to M4 E4 up to E4. So this is the equation for linear momentum conservation parallel to beam direction. And similarly, we have the parallel perpendicular to beam direction. This component is 0. Perpendicular component is 0 here. And for the ejectile, root 2 M3 E3 sin theta minus root 2 M4 E4 sin phi. So we have now 3 equations, and we can eliminate E4 and phi from these 3 equations. So if we eliminate, then we get an equation M3 plus M4 E3 minus 2 root M1 M3 E1 E3 cos theta plus M4Q minus M4 minus M1 E1 equal to 0. And this equation is quadratic in square root of E3. What is E3? It is the energy of the ejectile. So if you want to solve the equation for energy of ejectile at a particular angle, we can write this in the quadratic in terms of root E3, that is like ax square plus bx plus c equal to 0. And the roots of this equation then become like this. The equation, like root of that equation, will be x equal to minus b plus minus b square minus 4ac upon 2a. So root E3 equal to b plus minus b square plus w, where b and w are given in this fashion. These are actually from the previous equation. So you can write here, this is like a x square plus bx plus c. So this is a, this is b, and this is c. And in terms of, so you can write v and w. So v equal to root m1 m3 e1 cos theta, w is equal to m4q plus e1 m4 minus m1 by m4. So you can now find out the solution of this equation. That's called the Q value equation, which you can also write in this way, Q equal to this way. And then you can, so essentially what you want to know, that if a projectile is bombarding a target, then at a particular angle, what is the energy of this projectile, you can calculate. So the energy of the reaction products can be calculated for any angle and projectile energy. And this particular equation is applicable all types of reaction. It is independent of reaction mechanism. Whether you are studying elastic scattering, inelastic scattering, or you can studying compound nucleus reaction or a direct reaction, it is applicable for all types of nuclear reactions. So it is a generalized reaction, generalized equation for finding out the energy of a reaction product at a particular angle. And for energetically possible reactions, the root E3 has to be real and positive. So the outcome of this particular assumptions you will find, one can go more in details, which we will not go, and solve the equation for different types of reactions. In fact, I'll suggest you a book. If you want to go more details, you can see there is a book by R.D. Evans, Atomic Nucleus, very nicely explains all these aspects. Okay, now many a times we will discuss this energy in center of mass system. Whatever energy the projectile has, all of it may not be available for causing the nuclear reaction. And therefore, I thought I'll spend a little more time on finding out what is the useful energy. Like we have in chemistry, free energy is the useful energy to do the work. In nuclear reaction, it is the energy available in center of mass. That is the useful energy. So I will discuss these collisions in the laboratory and center of mass system. In the laboratory system coordinates, this is the scenario. That is the projectile M1, velocity V and energy E1, bombarding a target which is stationary. And so the center of mass of this system. Like if you have the mass here, so you can find out the center of mass at a particular coordinate, like m1 r1 plus m2 r2 by m1 plus m2. But here, this is a moving system, it's a dynamic system. So if the mass, the projectile is moving towards the target, the center of mass also moving towards this one. And after the reaction is over, this, suppose let us say in elastic scattering, the projectile and target will go in different directions, theta and phi. The center of mass remain between the a line in the line joining the two. So this x denotes the position of the center of mass after the collision. Now let us carefully see this, what I have written here, the momentum conservation, momentum of the system before collision. You can see momentum of projectile is m1v, which is nothing but the momentum of the center of mass, m1 plus m2 vc, where vc is the velocity of the center of mass. Let's combine system. So from this equation, you can find out velocity of the center of mass equal to m1 v1 by m1 plus m2. So this is the velocity with which the center of mass is moving. Now, if the center of mass is moving velocity v, vc, what is the energy tied up in motion of center of mass? Half m1 plus m2 vc square, where m1 plus m2 is the mass of the composite system. So the composite system is moving with velocity vc, and the kinetic energy will be half m1 plus m2 vc square. Now you can substitute vc by this equation. So it becomes half m1 plus m2 into m1 v1, m1 square v1 square plus upon m1 plus m2 square, and it can be given as half m1 v1 square v square upon m1 plus m2. This m1 plus m2 will cancel with this m1 plus m2, and so the kinetic energy of center of mass is given by m1 half m1 v1 square, half m1 v square is kinetic energy of projectile e1 upon m1 plus m2. You see here, this is the fraction of e1. m1 by m1 plus m2, this much fraction of e1 is spent in the motion of center of mass. This is the translational kinetic energy, and we'll discuss in the next slide. So this much energy you will find is not available for inducing the reaction. This much energy is tied up in moving the whole system in the forward direction. Half is m1 e1 by m1 plus m2. Now let us discuss the CM system, the center of mass system. In the center of mass system, the center of mass is stationary because the total linear momentum is 0 in the center of mass system. So observer is sitting at center of mass, and you will find the observer will see the projectile coming from one direction, target coming from another direction. So velocity of projectile in the center of mass system will be v minus vc, that of target in the center of mass minus vc. And after collision, they will go in different directions. So m1 will go, let us say, v minus vc, m2 will go with vc. So they will go at 180 degree in the center of mass system. Now, since the total linear momentum is 0, linear momentum of projectile m1 v minus vc, linear momentum of target minus m2 vc equal to 0. This is nothing but again the same equation, m1 v equal to m1 plus m2 into v. So vc equal to m1 v by m1 plus m2. Now let us calculate the kinetic energy in the center of mass system. In center of mass system, linear momentum is 0, but kinetic energy equal to half m1 v minus vc square plus half m2 minus vc square. Kinetic energy of this in center of mass, kinetic energy of this in center of mass. And you can see here, if you solve this, you will find half m1 v square minus half m1 plus m2 vc square. You can actually, there are one or two steps here. You can open this square and then club the vc terms. So you will get half m1 v square minus half m1 plus m2 vc square. And vc, you know, m1 v by m1 plus m2. So substitute for these, then this becomes half m1 v square m2 by m1 plus m2. You can see here m1 m2 by m1 plus m2 is reduced mass. You can also write this as half mu v square, where mu is the reduced mass. M1 M2 by M1 plus M2, or right now we will go ahead with this expression, M2 into E1. E1 is half M1 V square upon M1 plus M2. Now you see these two expressions. This is the kinetic energy in center of mass system, M2. So fraction of E1, that fraction is M2 by M1 plus M2. And the previous one was M1 by M1 plus M2 E1. So this much fraction is the kinetic energy of center of mass. This much energy is tied up in motion of center of mass. This much energy is available in center of mass to induce the reaction. This we call as the ECM. And this we will be using in subsequent lectures also. So ECM, the kinetic energy available in center of mass system, it is like the free energy for the reaction. So energy available in center of mass system, outcome of the previous lecture is ECM. E1 is the projectile energy in laboratory system. Energy available in center of mass ECM, fraction of E1 M2 by M1 plus M2, and that other fraction is called as required energy. So the other fraction is M1 by M1 plus M2. Essentially, it can be also called a required energy. Like when a heavy nucleus emits an alpha particle, then all the Q value is not available to alpha energy. A very small fraction, that alpha particle is giving a kick to the residual daughter nucleus, that is the required energy. So the implications of the center of mass system will be clear very soon. You can see here, let us apply this description to this reaction. Alpha plus aluminum 27 going to neutron plus phosphorus 30, the same reaction. Now, let us calculate the Q value for this reaction. The Q value is written in terms of, Q value is mass of projectile plus mass of target minus mass of projectile target minus mass of products. But what I am seeing here, they are not the masses, but they are the mass defects. So essentially, when we say 2.425 for alpha particle, it is M minus 4 atomic mass of helium atom minus mass number of helium atom 4 into C square. That's called the mass defect. So the mass defects are, for the purpose of energetics, the mass defect can be used. But for the purpose of kinematics, you cannot use mass defect. So there's the difference here. When we calculate the center of mass energy, we use the actual masses, or you can use mass number, because from the kinematics point of view, masses and atomic mass numbers are very close. From the energetics point of view, the mass numbers get cancelled out because the mass number is conserved. So delta A is 0. Before and the reaction, after reaction, there is no change in the mass number. And so what I am showing here is that mass defects. That is why you will find some positive value, some negative value, and so on. So alpha particle mass defect 2.425 MeV, aluminum 27 minus 17.197 MeV, neutron plus 8.071. So it is in the negative side, minus of mass M3 minus M4 for phosphorus 30. So this Q value becomes minus 2.64. Now, the energy of alpha particle from that 226 radium was 4.87 MeV. All this energy is not available for inducing the reaction. Out of this, only this fraction. So when I am calculating this fraction, I use the mass numbers, M2 by M1 plus M2. So 27 by 4 plus 21, 27 by 31, 4.87 into this fraction is 4.24. This is the ECM, energy available in center of mass, which is the useful energy that should be more than this, because this is negative Q value, means endoergic reaction. We need to supply energy. That energy to be supplied has to be more than this, and this is more than this. So when you want to compare this negative Q value thresholds, we need to compare with the CM, ECM. And also, now the compound nucleus that will be formed, let us say phosphorus 31, it will have certain excitation energy. So excitation energy of the compound nucleus is given by ECM plus Q. Energy in center of mass system plus Q value reaction is the compound nucleus excitation energy. Okay, so as I was just discussing, we may come across reactions where there may be negative Q value reactions, so they have a threshold. What is the minimum energy the projectile should have for inducing a reaction? So for endoergic reaction, which have Q value less than 0, the ECM must be at least equal to Q value. Because the Q value is negative, so ECM must be at least equal to Q value. So we can write a threshold energy for the reaction equal to minus Q, because Q is negative, so minus will become positive, M1 plus M2 by M2. So it is the inverse of that formula for ECM. So this threshold energy has to be equal to, it will be more than the Q value by this factor, because the remaining factor goes to required energy. So for this reaction, alpha plus aluminum 27, neutron plus phosphorus 30, which has the Q value minus 2.642 MeV, threshold energy minus Q into 31 by 27 equal to 3.033 MeV. So you can see here that for this reaction, there is a threshold of 3.033 MeV. But the projectile here is a charged particle, and the charged particle induced reaction, not only they have to cross the energy threshold, there is another threshold, that is the Coulomb barrier. And therefore, the Coulomb barrier also has to be crossed. So to calculate the Coulomb barrier for a charged particle induced reaction, we generate the Coulomb barrier formula, Z1 Z2 E square by R1 plus R2. If you have a projectile and target, let's say spherical particles, I can just show you in my blackboard. So if you have, so let us say they are touching each other. So this distance between the two, see R1 plus R2. So we see the Coulomb barrier, not to be confused with the center of mass velocity of the center of mass, will be Z1 Z2 E square upon R1 plus R2. Now, if you say spherical, if you take the this one as projectile and targeted spherical nuclei, then you can say R equal to R0 e power 1/3. So A is the mass number. And now so what I want to show here is that E square by R, that is the essentially Q1 Q2 by R. How does become energy in MeV? So you can write the charge of an electron in ESU 4.8 into 10 power minus 10 ESU square. You have to square it upon 10 to the power minus 13 centimeter. So ESU square upon centimeter will become ergs. And whatever comes in ergs, you can convert into MeV. So you can say 1 erg will be 6.24 into 10 power 5 MeV. And so this factor comes 1.44. What I have shown here is, it will show you this. Here, what I have shown, that whatever I derived in the previous one, that will become 1.44 as the factor which will straight away come in MeV. So you will be using this in your numericals, this factor 1.44 to calculate the Coulomb barrier in MeV. So Z1, Z2 are the atomic number of projectile and target. R0 is the radius constant, which is can be given as 1.5 Fermis, and then the mass number of projectile and target to the power 1/3. So using a calculator, one can calculate the Coulomb barrier. So for this system, alpha plus aluminum 27, 1.44, 2 into 13 upon 1.5, 4 to the power 1/3 plus 227 power 1/3 becomes 2.787 MeV. So now ECM has to be equal to Coulomb barrier. This is the condition that that means to cross the Coulomb barrier, the energy in center of mass system must be at least equal to Coulomb barrier. So if you want to calculate now corresponding threshold for a Coulombic reaction, then E threshold for Coulombic point of view, Vc into M1 plus M2 by M2, 2.787 is the Coulomb barrier, Vc into 31 by 27, 3.20 MeV. You can see here, based on the energy threshold for this reaction, 3.033 MeV energy will do. But based on the Coulomb barrier, you require 3.2 MeV energy. So when you are discussing the charge particle induced reaction, not only that we have to consider the energy threshold if Q value is negative, we have to also consider the Coulombic threshold and arrive at the threshold energy. Whichever of these two is higher, that is the threshold. Okay. So lastly, I will just touch upon this aspect of cross-section of a nuclear reaction. The cross-section, which we denote as sigma, is a measure of the probability of occurrence of a nuclear reaction. You can see that it is a cross-sectional area. You can see that this represents the cross-sectional area offered by the target nucleus to the projectile in this reaction. So a very simple diagram, if a projectile, small projectile is coming and hitting a target which is much bigger than this one, then the cross-sectional area in a plane vertical to this direction is the circle, and the circle will have an area pi r square. So that is why we say the units of cross-section is barns, and one barn is 10 power minus 24 centimeters square, because the dimensions of the nuclei are of the order of 10 power minus 13, 10 minus 12. So the cross-section for nuclear reactions is represented in terms of barns. This is a very small quantity, so we will use always barns. Now, if we have a projectile which is comparable to the size of the target, then what we have, this R will not be this R of the target, it will be R1 plus R2. So you'll have a target projectile here. So radius of that circle, cross-sectional area for this reaction will be R1 plus R2. So you have to draw a circle of R1 plus R2. Area of that circle will be the cross-section. A very crude explanation of cross-section. We will discuss further. For example, for neutron-induced reaction, the low energy neutrons have wavelength of neutron much larger than their nuclear dimensions. So for the neutron-induced reaction, reaction cross-section is given by pi r plus lambda cross square. That lambda cross is the reduced wavelength, h by p, p the root 2 mu e, the momentum, linear momentum. So r plus lambda cross square. So not only that, we have to consider the radius of the projectile target, but also the wavelength of the projectile, because if the wavelength is comparable to target, then wavelength becomes, essentially it is giving the distance in which the projectile is available. So neutron having large wavelength is present in a large distance. So in fact, for low energy neutrons, lambda is very, very high, of the order of angstrom. Thermal neutrons have wavelength in the angstrom range, because you can do neutron diffraction of crystals. So that means the neutrons have to have wavelength of the order of angstrom. And that is why you will find that the low energy neutrons have very, very high cross section compared to pi r square. We'll discuss this further in more detail in the next lecture. So the rate of a reaction can be given by number of atoms of target per cc, atom density, the cross section, and the flux. The flux is number of neutrons per centimeter per second. So you can see here the unit of this is atoms per cc, centimeter square, neutrons becomes per second. So that how many reactions are occurring per second and sigma phi. For charged particle induced reaction, below the Coulomb barrier, reaction cannot take place. So ECM has to be more than or equal to VC, and therefore we'll derive in the next lecture this formula. Cross section for charged particle induced reaction is given by pi r square 1 minus VC upon ECM. So while for neutron induced reaction, cross section decreases with increasing energy of neutron. For charged particle induced reaction, cross section is 0 up to a certain energy and then increases with increasing energy of the projectile. Here, the rate of the reaction is given in terms of number of target atoms per centimeter square, because in the case of neutrons in the reactor, entire target is irradiated with neutrons. In the case of target, in the alpha charged particles, only a small area is irradiated with the charged particle because the beam dimensions are finite. I is the number of particles per second. And so again, you will find this becomes equal to the number of reactions occurring per second. Okay, so that comes to the end of my presentation. And I will recommend this book if you want to get more details into whatever I have covered, particularly the energetics part of this nuclear reaction. There is a book by Atomic Nucleus by R.D. Evans, published by Tata McGraw-Hills in 1955. And if you go to Google, it is freely downloadable. So it is a very good book for understanding the basics of nuclear reactions. One can use this, refer to this book for further reading in this area. And there is a book by Friedlander, Kennedy, Miller, and Macias, third edition, 1981, Nuclear and Radiochemistry. This also gives a very good account of the subject of nuclear reactions. That's all I had to say.